All right, we are on to learning task 3 here for our DC generator characteristics, and we're going to go and take a look at the different operational characteristics of DC generators. We talked about the basic components of them. We talked about the builds in the first two. Now we're going to go and talk about the 3 main types of generators that are going to go and be apparent. And we are going to go and have our series that we are going to have. We will have the shunt connection generator that we will take a look at, and then we're going to go and have the compound, which is going to go and combine that. These two are each going to go and have certain benefits that we're going to have. We'll see inside of the series certain benefits. We'll see inside of the shunt certain benefits, but there's also going to be drawbacks inside of them. And so then what we're going to be able to do is we're going to be able to combine them both, and by varying the amount of series or the amount of shunt, we're going to be able to get a bunch more of different subsets of generators, or different types of compounds that we're going to be able to get out by combining these two in varying amounts. Before we begin, though, we have to go and talk about a couple of NEMA standards. NEMA is the National Equipment Manufacturers Association. You should be familiar with the fact that NEMA is a standards body that designs equipment, or that doesn't design equipment, but though that goes and chooses what the stamps are going to be on equipment when I call things L1 versus T1, etc. We follow those standards so that anybody can pick up anybody else's piece of equipment and understand what those components are going to go and be. We're going to go and take different types of fields that we are going to go and have. We're going to have armature fields, coils. We're going to go and have field coils. We're going to have shunt series coils. And we are going to go and identify them with letters. Those letters are going to go and be A for armature. We are going to go and have F for shunt fields. And then we're going to have S for series fields. So as soon as I take a look at a winding, I'm going to go and identify it as being shunt or series off of the letter. We'll go with an F off of this one over here. The other thing that we are going to have is we are going to go and have subscripts on them. So if this is an F winding that identifies as being a shunt winding, then I'm going to go and have an F1 and a F2. And the F1 and the F2 over here are going to go and identify the direction of current that we are going to have going through here. We are always going to go and have electrons flowing through. Well, I shouldn't say always, but what should be set up is that they go through from the 2 to the 1 is what we are going to want to see. So anytime that we're creating a standardized connection, because we're trying to standardize, we're preventing things from being, set up weird so that anybody can service these things, our standardization is going to be for us to go and have 2 to 1. Now, in some cases, we are going to go and have components that are going to be sources. Things like our armature are going to generate the value of voltage, which means that in a source, current flows through from positive to negative. Just erase a bunch of this here so we can start sketching some of that up as well. So all groundwork we have to lay first. So we'll go and take an armature over here. We'll identify this thing as being an A. We'll stick a couple little brushes on the side over there. This is going to be an A. We're going to call this thing A1, and this is going to be A2. Current has to flow through this thing from my 2 to my 1. So if I take a look at this, I would be able to go and identify which side is going to go and be my positive. And that's going to be identified off of the fact that current flows through from positive to negative through a source. Positive to negative through a source. And then outside of a source, it then flows from negative to positive through a load. Let's put a resistor down here. If we take a look, anything that's connected across here is going to receive the same polarity. Because this is a negative, this would have to be a negative. Because this is a positive, this would have to be a positive. And it just makes sense when we follow that through now that my current goes positive to negative through the source, and then it is going to go from negative to positive through the load, because my current always has to form a complete loop. Okay, we're always looking for that. So my load can be multiple different things, though. Sometimes my load is going to be an actual resistor. Sometimes my load is going to go and be another winding that is going to be generating magnetic fields, like my series and my shunt windings. In those cases, we want to pass our current through from negative to positive. So we want to go through, we would have to go and say if it's going to go through, this would have to be my negative, this would have to be my positive, if I were to be attaching that as my load off of here. We'll see this in situation in each of these as we go through from component to component. There is also going to be a couple of conventions that we are going to go and utilize. The clockwise rotation that we are going to go and utilize. Clockwise meaning that going around the same direction as arms on a clock. For those of you that only have digital devices, that is going to be going around like that. It is going to be observed from the non-drive end of the machine. By non-drive end, what they mean is that if this was my generator itself, it's going to be circulator, and I have got that thing attached to, I'm going to be very bad at drawing this, but let's say it's attached to my engine over here. There's a couple engine components and stuff like that. There's my engine, there's my generator. What I'm going to be doing is I'm going to be observing clockwise rotation from the non-drive end. This just makes sense. If I were to open this up, I'm never going to remove, well, I shouldn't say never, but hardly ever am I going to remove the engine blocks so that I could go and look into this end of the generator. That would be impractical. Most of the time, I'm going to go and stand over here where the engine is not in the way, and I'm going to go and look into this genset. So we're going to go and deal with, for clockwise rotation, observe from the non-drive end. That means that we are dealing with a clockwise rotation off of this. Then we are going to go and have A1 that is going to go and be negative. So don't worry too much about exactly what is going on for that, direction of rotation. We've talked about direction of rotation. It's important. But for now, you just need to go and focus off of these things here, that my 1s are going to go and be my negative on my supply. My 2s are going to go and be my positive because we're flowing current through from 2 to 1 that are going to be inside of here. As far as components inside of here, this end of the generator is where I'm going to go and have all of my brushes and my commutator. Because I do have to maintain the brushes and commutator, I wouldn't want to have to go and remove the engine in order to get at brushes and commutator. So I'm going to go and place them at the end that's going to be easy for me to go and access. In most cases, you always will have a manufacturer out there who makes a dumb unit that might not follow that convention. And then when you take it apart, you're just going to be super upset about it. But by and large, this is what we are going to go and see. Okay, let's go and talk about our very first generator, which is going to be our shunt generator, which is going to have an overall characteristic that my volts are going to drop with loading. Okay, ultimately that's what we are going to be looking at. Current flows through my components from 2 to 1, so I'm going to go and draw a 2 to 1 through here. I'm going to go and draw a 2 to 1 through here as well, and then I'm going to go and have a section over here where I can go and have my load connected across over there. If I were to go and connect a load across, this is where that load would be connected across from here to here. Ultimately, this is a load. This is not a source. It is an electrical load that is creating magnetic flux that this thing can then go and rotate inside. The prime mover rotates it, but this is going to be an electrical load. Because it's an electrical load, we have current that is going to flow through from negative to positive. And really, if you go and trace this out, if this is a negative here, if this end is attached to it, it would have to be negative. This is a positive here, this attached to this would have to be a positive as well. Our terminal box is going to look something like this, where we are going to go and have our lines that are going to go and feed out. And they do actually have terminal boxes on these things, or in some cases they're just going to have numbering that's going to be on the terminals, where you are going to be able to go and select your connections inside of here. Over here for a A1, A2, etc., you could just draw your components across here if you really wanted to. I know that my current has to go and travel through from a 2 to a 1, so I know that I would have to have current going like that inside of the terminal box, and then it has to go through from a 2 to a 1 through here as well. So this would be a load. You can see that direction of current, as well as it would have to go from a 2 to a 1 through my external load there as well. You see that both of these, this would be a path going through, delivered from that generator coil. This would be a path as well, delivered through the load and coming back up through that generator coil as well. Always, always, always just start with making those directions of a current 2 to 1 and then match these lines up. When I go and operate these things, a couple of things are going to go and happen. Okay, let's talk about this load over here. As soon as I connect a load across here, we're going to go and get current flow that is going to get delivered out of here and go down through here and come back up through here. It has to form a complete loop. It goes back to the source over there. Because I've got that current flowing through there, I have got current that is flowing through here. Now we know that we've got this formula, V is equal to I times R. We can go and use this to go and figure out what the voltage is dropped across any component. Is there going to be resistance in here? Absolutely. It is a physical component made out of physical wire. So there's going to be some resistance in there. Is there going to be current flowing through? I mean, we just traced out this blue path over here. There is going to be current going through. So is there going to be a voltage drop across that generator? Absolutely. There is going to be a voltage drop across that armature. And what we are going to see is that that voltage drop, as my current goes up, the voltage drop across here is going to go up as well. We might have a generator. We'll give this thing a rating. Let's say that this thing is rated to go and deliver 48 volts DC. That's what I'm taking out of this thing. If I have got 48 volts DC with no load attached to this thing, so I'm just spinning it, the only load that I would have at that point would be this small amount of load going through that field over there. As we go and increase the amount of load that we're going to take off by taking this over here, we increase, we add in another current path. So we've got this blue current path now that's going to go through like that. We're going to increase the amount of current that is flowing through there. Therefore, we're going to increase our voltage drop. This thing is still going to go and put out 48 volts, but now it's going to go and drop some of those volts. Let's say it drops 2 of those volts. It's going to drop 2 of those volts before it ever leaves the winding. Still puts out the same value of voltage. EG is equal to BLV. We've got the same flux density, same length, the same velocity this thing is turning at if we've got a good prime mover. So it's still going to put out the same value of voltage, but now we're going to drop some of those volts just across the copper before we leave. So 48 volts minus 2 volts would mean that now I'm going to be left with a value of 46 volts that I'm going to go and have on my outputs of this. If I've got 46 volts that's on the output, that means I'm going to have less current that's going to follow through my field, which means that my beta is going to go down as well. I'm going to go and have, a little bit of a drop in beta, which means my overall generated value of voltage is going to go down as well. And so what we start to create is this self-feeding problem, where as I go and take current out of this thing, we're going to go and drop volts inside of here on the actual copper itself. We start to drop those volts. Because we drop those volts, we're going to go and get less flux that we are going to go and have as well because we feed less through here. And so overall, I end up with a line that's going to go and look something similar to this over here, where I'm going to go and have a terminal voltage that is going to go and start really, really high when I've got no load. But then as I go on load, I'm going to see that my voltage, my terminal voltage, is going to go and drop. And we see that drop happening as my current starts to go and rise until I get to what we would consider to be full load voltage off of these. That drop that we see over there is going to be critical, this value over here, because this is going to go and tell us something that's called voltage regulation. And voltage regulation is really going to be how bad is this thing at maintaining a steady value of voltage. Ultimately, we would love it if we could go and keep a steady value of voltage no matter what the current is going out there, but we don't live in a perfect world, so we're not going to go and see that happening. What we'll have is we're going to have this new formula for percent voltage regulation that is going to be my E no load minus my E full load. So I'm going to go and have this value over here. This is my no load, NL. This over here is going to be my full load over here. I'm going to go and find what that value is, the difference between those two, and then I'm going to go and find out what percent that is out of my E full load, the amount of voltage that I'm generating across here. We'll give this thing a couple of values. We'll say that this thing has got a no load voltage of 50 volts. It's got a full load voltage of 48 volts that we are going to go and have. So my difference between those two is going to be 2. This over here, I can do this as a values up top here. It would be 50 minus 48. That's my full load over top of my 48. So it would end up being a value of 2 divided by 48. 1 second. Should have picked easier values. 2 divided by 48 gets me to a value of 4%. I'm going to have a 4% voltage regulation. In other words, my voltage varies by 4% overall, depending upon how heavily I'm going to go and load this. I can see up to 4% more voltage as I drop my load on. We do have to be careful with this because as we lightly load, our terminal voltage goes up, and so we have to just be careful that the load we connect to it can handle that sort of a rise. Going back to our shunt generator here, one more time, just erase all of this. We don't need that anymore. This drawing that I have over here, if you take a look at this drawing, you will see that this drawing is going to go and be the same drawing as what you would have seen inside of the last learning task. This one's now just kind of laid out as a visual representation, as a diagram. This one here is more of a visual one, but if you follow it through, you can see that once again, we are taking our current through from 2 to 1. So we identified the 2 to 1, we'll drive that over there, and then I'm going to go and identify this as being a 2 to 1 like that as well. And then they show the field rheostat here. This one here, they did not go and show the field rheostat, but if we go and compare that with this, they show that the field rheostat is connected across F1 over here. So really, if they wanted to go and make this one truly the same as the other, they would have to go and place that field rheostat in right over there. Either way, you can compare one to the other. You're going to see that they're the exact same connections. Out here is going to be my external load. My load 1, my load 2 are going to be these two terminals here. A shunt generator will have a voltage that it can generate even when there is nothing that is going to be attached to it, because when there's nothing attached to it, I'll just erase this value right over here. Even when there's nothing attached to it for that it's feeding over here, it is still going to go and have a complete path for current going through here. Because that complete path for current goes through the field, it is going to go and generate that EG is equal to BLV. We're going to go and get that flux, so it is going to go and generate and give us values of voltage off of it. We're going to take a look at another generator that we have over here, which is going to be called my series connected generator over here. The series generator, if you take a look at it, where is my complete path for current flow? Well, my complete path for current flow in a series generator is only going to go and happen when I connect a load across it. If that load does not exist, I will have absolutely no way to go and complete this. And if I don't complete this, if I can't put that inside there, I've got no current flow. If I've got no current flow, then how much flux am I going to go and get off of that one? Let's go with that other EG formula. EG is equal to my K phi N over here. Similar to the BLV one, but where I'm going to go and have my machine constant, the K, the type of machine it is and how it's been built, my phi, which is going to be my flux, and then my N. Well, what is that formula for phi? Phi is ampere turns is what I'm going to go and get for my flux. If I have got no complete path, I'm going to go and have 0 amps that's going to be going through here. If I have got 0 amps, that means that I'm not going to go and have any flux, which means that I'm going to go and generate 0 volts that I'm going to go and take across here. Technically speaking, I'm going to go and have no volts that's going to be across there. In reality, you might get a tiny little bit of volts across there just due to the residual magnetism that is existing inside of here, even though we don't have anything that's going to be connected to it. Okay, talking about our connection that we are going to go and have. When I have got no load off of here, let me just put that one back in there, K phi N. When I've got no load across there, we see that we are going to go and have 0 volts. That is going to be across it. In reality, it's going to probably be a very small amount of volts that's going to be across it. As soon as I start putting a load across here, we're going to start to see volts. Now I'm going to start with a very high value of resistance. If my resistance is really high, therefore my I must be low. I is equal to E over top of R. So here is my E, my generated voltage is coming off of that. If I have got a very high value of R, I'm going to have a low value of I. And if I've got a low value of I, that means that my ampere turns is also going to be fairly low, which means that my flux up top over here is also going to be very low, which means that my voltage output is also going to be very low. So if we start with a lot of resistance in there, we are going to go and have a low value of voltage. If, however, I drop my load resistance, so now my load resistance is low. If my load resistance is low, then I am going to go and have a high amount of current that is going to go through here. If I've got a high amount of current, my ampere turns are going to go high, which means that my phi will go high. And if my phi is high, my generated value of voltage is also going to go high off of this. what we get is we get this really, really funky looking curve like this that's going to go and start out at a value with no load. It's going to start out very, very low. Technically, it should be at 0, but because there's residual magnetism, that residual magnetism is going to go and give us a small amount of generated voltage. We connect a load across, and then we're going to go and see this whoosh, this rise in voltage. It's going to come up, and then we're going to start to hit this point where any increase in the amount of current going out is no longer going to give us any more useful flux. We start to hit that point of saturation. Once again, if you take a look at this, you should be able to start to see that hysteresis curve coming out of this thing. We start to see where we have got, these rises in voltage, this rise in current that is going to go and give us a rise in magnetism, but then the magnetism starts to go and saturate. Is this going to be a useful generator by itself? Not always going to be a very, very useful generator. The more load that I put onto this thing, the higher the voltage is going to be that it's going to generate. There's relatively few loads that are going to work well with that. We are going to go and use this terminal, though, or use this termination to go and compound some of our other stuff, because we see that my shunt drops with load, whereas my series rises with load, which means that if I can go and put those two together, I'm going to start to go and get a steadying on once I start to go and, compound my generator off of here. Going back to this one over here, last thing that we want to look at on here is going to go and be the connection that I'm going to go and have in here. We're going to go and compare that to my connections that I had in my previous learning task number 2. Learning task number 2, we had the same connections shown, where we had the A2 and the A1 and then my loads, and they show that once again current is going through from 2 to 1 and from 2 to 1 over here. If you compare that one to this one over here, you see there's the exact same thing. My A1 is connecting to my S2. My A1 is connecting to my S2. This one's just a pictorial representation rather than the schematic diagram that we would see for this one. Okay, so by itself, not very, very useful because my voltage rises. So that's sizes. I don't know. I could spell. Rises with load off of these. Okay, let's talk then about the compounding of our generators. We are going to be able to go and do a couple of different types of compounding that we are going to go and create. We're going to go and have ones where my magnetic fields are going to be aiding each other. That's going to be referred to as being cumulative compound, where both the S1 and S2, the magnetic fields of those are going to be helping each other out. We are also going to have ones where I'm going to go and have differential types of, oops, sorry, wrong one there. Nope, maybe is that one the wrong one? Hold on, I gotta go one further down here. No, I don't have that one there. I'm only showing the cumulative compound ones inside of here. I don't have the differential compound ones inside of here for some reason. Oh yeah, no, I do have the differential. These are my differential ones over here. I just lost that bottom part of there where it says differential compound. But I'm going to go and have differential ones where I'm going to go and have fighting between my fields rather than aiding between my fields. Let's talk about the cumulative compound and the differential compound. I'm also going to go and have short shunt and long shunt. Short shunt is going to go and be a shorter connection that is only going to go and take place going across the armature. My shunt is going to only go across the armature itself. Whereas long shunt, my shunt field is going to go across the combination of armature and series at the same time. Excuse me. All right. Let's start with the cumulative compound because the cumulative compound is going to go and be my more common one that I'm going to go and have. We do also go and consider that this field, the shunt field, is going to go and be my main field. We're going to go and have makeup amount of flux that we are going to go and take in from these. In other words, that we're going to use that series field as more of a compensating field than as a main type of field that we are going to go and have. Looking at these ones over here for my cumulative compound generator, I can go and follow through with my 2s to 1s again. So I'm going to go and see that this goes through from 2 to 1. This goes through from 2 to 1, and then this goes through from 2 to 1 as well. I see that on all of these, 2 to 1s, 2-to-1s, 2-to-1s. These are going to go and be sources, the actual armatures. These are going to go and be loads, the fields. The fields are going to always be loads, therefore they are going to go and have current flowing through from negative to positive. So I can figure out which is negative to positive, etc. on them. Connections inside of these, you should be able to identify which connections we have just off of the way that my current is going to go through. Once again, anytime that you're starting to look at these, look inside of this terminal box and say, this thing here is going from a 2 to a 1. And so then I can go 2 to 1 through there. And then I can say that current would be entering there, going 2 to 1 in there, and 2 to 1 on the outside. See that everything is going 2 to 1, so it's going to be a cumulative compound, and it's going to be my short shunt because, my long shunt, because I'm going through the series, and then I'm just taking that shunt field back across this thing. The cumulative compound in short shunt and long shunt is just going to go and vary the amount of series that I'm going to go and have. This one over here, because it is running through here, the more armature current that I'm going to go and get out, the more that this voltage is going to rise, while at the same time, this voltage is going to be dropped across it. This one over here is going to have a relatively constant amount of voltage. But then once I start to take load current out, I'm going to simultaneously be getting the rise out of this while I'm getting the fall out of this. And we classify them into a bunch of different curves over here. Flat compound, over compound, under compound, and then differential compound that we are going to go and have. Let's talk about the over compound first. Over compound is going to be increasing amount of flux that's going to be flowing through my armature current flowing in the series winding. So I'm going to basically give myself more series winding, which means that I am going to go and have a relatively, for my flat compound, a relatively flat going along here, and then it's going to start to kind of drop away. Right about here is where we are looking at being our amount of load, or rated amount of voltage that I'm going to go and have over here. If I take a look at my shunt, I see that my shunt over here, they're giving me just a plain shunt type. We saw that that thing drooped away. Here's my terminal value of voltage that I see over there. Normally, my shunt would go and drop like that. My series is going to go and be a rise. That's going to go and look like that. So these two blue lines are really what we are combining in varying doses. This one over here, for the flat compound, we are giving ourselves just enough series to go and counteract most of that shunt, so that we end up being a tiny bit up, but more or less flat, and we end up a tiny bit down by the time we get to our rated value of voltage off of it. If we compare that one with my over compound, I'm going to go and add in a bit more series field. When I add in a bit more series field, then I'm going to go and end up with, as I get to this terminal voltage, I'm going to go and get a larger value of voltage, what we're seeing along this line. I should just highlight along the over compound line. That over compound line is going to make up for transmission drop. DC is notorious for dropping values of voltage. That's why we prefer AC for distribution. Because it is going to drop, I'll use an over compound if I know that I've got a genset that's going to be sitting right over here, and then that I'm going to go and have a long run from where that genset is over to the actual load. I'll want to go and over compound it, bring it up higher, so that the voltage drop that I'm getting across the lines over here is going to be made up for, so that by the time I get down to the load over here, I'm back to my regular value of voltage. We want to give these things values. We could go and say that this is a 48 volt load, but that I'm going to be delivering 50 volts out through an over compound, but I'm dropping 2 volts over top of the line, which gets me to this proper 48 volts down here at the load. Under compound, if I go and under compound a generator, that thing is going to go and have less series and a little bit more shunt. I've just got a small amount of series to go and make up for it. It's going to be better than my shunt, but it's not going to be fantastic. It's basically a cheap transformer connection. I don't, want to have it as bad as the shunt, but I don't also want to invest a lot of money in getting, proper series winding, so I just kind of go with this under compound. You're not going to see a load of those. It's mostly going to be flat compound or over compound that we are going to see out of these ones. The last one that we are going to go and have is going to go and be my differential that I'm going to go and have. And the differential is going to go and be based off of a differential type of connection. If I take a look at this connection over here, I'm going to take a look. I've got my current flowing through from 1 to 2 through here, but then from 2 to 1 going through here. So if I were to look at these as being actual windings, one of these is going to go and have a north to south. The other one's going to go and have a south to north. And depending upon, south to north, depending upon which of these is going to be the stronger one, we are going to go and have more of one versus the other. If I go to my differential compound, and if I've got a very large amount of series windings on my differential compound, as I load up, all of a sudden I'm going to go and get a reversing value of voltage that's going to be dropping away. And then we get to this one that we have over here, which is going to be my differential connection over here. Differential connection is really only got one specialized use, and that's going to go and be welding. DC arc welding, where I need to go and have a high value of volts to strike that arc. I've got 0 amps until I strike that arc. I get a high value of volts, and then as soon as I start dumping amps into my workpiece over there to go and melt the metal and fuse it all together, I'm going to see that value of voltage drop down low. This is what you want in welding. High arc to start, and then the voltage drops away and the current goes high so that you can actually run everything through there. Not useful for anything other than that. Usually, as we said before, it's going to go and be this cumulative compound that we are going to see more than anything over here. Last thing that we're going to go talk about is going to be my diverter and my field rheostats. Let's just go and take a quick look at diverter and field rheostats over here. What my diverter and field rheostats are going to allow me to do is adjust the amount of compounding that I'm going to go and have inside of my generator. So what I might start with is I might start with a generator, and this is, a more common application of it, is I'm going to go and wind my generator so that I'm going to go and be over compounded. Because it's easier, it's better to be looking at it than looking for it. I'd rather have too many volts that I can cut away than to have too few volts that I cannot make up for. So I'll start in a lot of cases with a DC genset that is going to be over compounded straight from the factory. That's how they go and build this. But then what I'm able to do is I am able to go and vary the amount of series field. Remember that the series field is the one that is raising my voltage, so allowing me to go and get over compounded. What I can do is I can go and take some of my current, and instead of sending it all through here out to the load, what I'm able to do is I'm able to use this diverter rheostat, which is going to be a beefy giant rheostat, but I'm going to be able to go and take that and I'm going to send some of it. So I'm going to split it down, which means that this current over here is going to get a little bit smaller. And because it gets a little bit smaller, the effects of my series field are going to get a little bit weaker. In other words, if I want to have less of this over compounding and I want to bring this thing closer down to flat compound, I'm going to divert more of my current away from the series field. I'm going to take it up through there. I'm also going to be able to go and adjust my field rheostat over here for my shunt field. Now the shunt field's rheostat, we are going to go and use that to adjust what we would have with nothing turned on to the generator. Basically, it's going to be my starting point of the load over here that I'm going to be adjusting with that. If I were to go and take a look at these, this one is going to be my field rheostat. The point over here is going to be adjusted by my diverter rheostat. So one of these is going to go and select where I'm going to start. Anywhere along this line inside of this range. By using that field, I can adjust this because we have got EG is equal to my K phi N over there. I'm just going to adjust the amount of current going through that field so I can adjust the amount of flux, so I can adjust the amount of generated value of voltage. That one is corresponding to this one that we have right over here. It sets the start of that line. The end of the line, how far I'm going to go and compound, is going to be done by that diverter. If I divert a lot of current around the series field, I'm going to go and drop this thing. I'm going to take it down all the way to, oops, sorry, I went too far there. I'm going to go and divert a lot of current. I'm going to go to under compound. If I don't divert very much current at all, I'm going to go to over compound. So my diverter is really going to allow me to go and make the variation between these 2 points, which allows me to do a lot of really funky stuff using these 2 rheostats, because I can go and do stuff where I can bring this point up really, really high over here and bring this point down really, really low. So I can go and run this thing closer to a differential, or I can adjust them the opposite way using the same generator and I can now go and have this one low and this one relatively high, and I can go to a relatively hot over compound that I would have off of these ones. All right. Last thing to talk about is just going to be the long shunt versus short shunt actual effects. Relatively minor, whether we pick to do long shunt or short shunt, because ultimately when we're running at full terminal voltage, we're going to have the full amount of our shunt and series field in there. Obviously, compensated for by my diverter rheostat and by my field rheostat that I'm going to go and have. So it's not a huge thing, whether I'm going to choose to do short or long. However, if I do want to go and get maximum shunt field excitation, in other words, I want to get the strongest amount of flux inside of here to go and start this out, then what I'm going to want to do is I'm going to want to connect that directly across the source of the voltage. If I connect it across this is a low over here, so I'm not going to be able to go and build my flux as quickly. So it's better for me to go and connect it directly across like that, short shunt for this. Okay, just an easier connection to go and build voltage. Although, once again, it's potato, it's not a lot of difference from one to the other. All right, that covers off the bulk of our theory on these. We don't have a lot left to cover on DC generation. We just got to go and, well, no, actually, I think that's the very last one here on DC generation. Never mind, I think it is. All right, good enough.